Hi, everyone. So we are on page number 9, and we're going to start to have our conversation about the periodic table. So we'll spend a few days talking about how the periodic table is organized, how it was created, and what you can learn from knowing where something is located on the periodic table. So the history of the periodic table starts way back in 1892 by J.W. Dobbenreiner, who was the first one to really publish a classification system of the elements that we knew about at that point. Up until this time, really all we had was like an alphabetical list of the elements that we knew about, but there wasn't really, it was alphabetical. It didn't tell you anything else about the properties of those elements or how they might react. So Dobbenreiner took all the elements that we knew about at the time and put them in triads or groups of 3. So things that would rust, he put in a group of 3, and then gases, he put in a group of 3, and things that were blue, he put in a group of 3. So it was a good start, but it definitely had a far way to go until it achieves what our current modern table looks like today. In 1896, Dmitry Mendeleev was the first one to really publish a periodic table of the elements. Now, Dmitry Mendeleev was a teacher. He was trying to come up with a better way to teach his students about the elements. So what he basically did is he took functionally index cards, and on each index card, he wrote down everything that he knew about each element. So every element had its own index card. And he started rearranging these index cards and trying to make some sort of pattern out of them. And what he settled on was a periodic table in groups based on sets of repeating properties. Now, Mendeleev's table was arranged in order of increasing atomic mass. And part of the reason for that is, again, you think about 1869, we didn't know about subatomic particles yet. We hadn't had Thomson's cathode ray tube experiment to discover the electron. Rutherford had not done any of his experiments yet. It's almost 40 to 50 years before those experiments took place. So he arranged his elements in order of increasing mass. Now, just kind of a side note, interestingly enough, that exact same year, another scientist by the name of Lothar Meyer published a periodic table that looked almost identical to what Dmitry Mendeleev published. And you might be thinking, like, whoop-de-doo, 2 men published the same thing. They didn't know each other. They had never heard of each other. There was no copying going on. They independently arrived at basically the same idea and the same conclusion. And that just adds some validity to what was happening when you have 2 independent scientists coming up with the same idea over time. Now, what we have here is sort of a version of what Dmitry Mendeleev's table looks like. And obviously, it doesn't look identical to our modern periodic table, which is right here. But you will notice some similarities. For example, this first group, this first vertical column, hydrogen, lithium, sodium, potassium, rubidium. Hydrogen, lithium, sodium, potassium, copper's in there, but then rubidium. We have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine going in this period 2 here. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine in period 2. So there are definitely some similarities, but what makes Dmitry Mendeleev's table so remarkable is that he left blanks and with just question marks. And he said, I think someday we'll discover an element with a mass of 44. We hadn't discovered it yet. And he ended up being right. He predicted the existence of certain elements that we didn't know about yet. And we ended up finding an element with a mass of 44, which is scandium right here, Cs. So it was an excellent, excellent place to start. Fast forward to 1913, Henry Moseley. So this was right around the same time when Rutherford was doing his experimentation. What Henry Moseley is famous for is he discovered that every element has its own unique atomic number. Now, atomic number, remember, is equal to the number of protons, and that defines what element you have. Carbon is carbon because it has 6 protons. That's what makes it carbon. If it had 7 protons, it wouldn't be carbon, it would be nitrogen. So what happened then is that we reorganized the periodic table. So our modern periodic table is arranged in order of increasing atomic number. I'm going to put in parentheses here, number of protons. Okay? So it's a little bit different than what Mendeleev did. His was by mass, ours is by atomic number. Now, our modern periodic table, we have 7 rows, also known as periods. Now, when we use the term rows here, we are referring to horizontal rows going right to left, okay? Now, these periods correspond to the number of occupied principal energy levels, PELs, okay? So everything that is in period 1 has 1 energy level that has electrons in it. Everything in period 2 has 2 energy levels. Everything in period 3 has 3 energy levels in the ground state. That can change when you go excited. But you can also see just by looking at the electron configurations that that's true. Everything in the 4th period has 4 energy levels, okay? The periodic table is also split into 18 columns or groups. So these would be vertical, going up and down, okay? So within a single column, you are going to see similar chemical and physical properties. Parentheses here, because elements have the same number of valence electrons. Now, this is not a hard and fast rule. There are going to be exceptions to this. But typically speaking, within a single group going vertically up and down, everything in group 1, for example, has 1 valence electron. If you look at the electron configurations in all these elements, everything in group 2 has 2. Everything in group 13 has 3, 14 has 4, 15 has 5, 16 has 6. Again, the transition metals in the middle get a little funky, as they do, but pretty much the rest of the table, if it's in the same group, it's going to behave similarly to the other elements in that group because it has the same number of valence electrons, outermost electrons, okay? Which brings us to periodic law. When elements are arranged in order of increasing atomic number, there is a periodic repetition of their physical and chemical properties, which means when you put them in order based on atomic number into a periodic table, there are going to be patterns. Everything that is shiny is kind of in the same spot on the periodic table. Everything that is really reactive is in the same spot. Everything that has color is in the same spot. Everything that's a gas is kind of in the same spot. So there are definitely patterns that are going to exist that we're going to spend the next few days talking about. Now, we briefly also had previously talked about metals, nonmetals, and metalloids because you guys needed to know that in order to do the naming, right? So let's talk about metals a little bit more. Metals account for 80% of the periodic table. They are good conductors of heat and electricity. It has to do with the fact that their electrons can move around easily. And when you can get electrons all flowing in the same direction, they can carry electrical charge and current. They have high luster. Remember, the word luster means very shiny, typically speaking. They are solids at room temperature. There's one exception to this that some of you might be familiar with, which is mercury. So Hg is the abbreviation for that. Mercury is a liquid at room temperature. Mercury historically used to be used for thermometers. In fact, if you have a really old thermometer and it has like a silvery liquid in it, it's mercury. Now, we stopped using mercury for thermometers because we figured out mercury was very toxic and over time caused brain damage. So we don't do that. Thermometers now, the ones with the red in them, that's actually just rubbing alcohol that's been dyed red. So if those break, it's less of a problem. They're not toxic. Metals also are ductile, which means they can be turned into wire. Copper is particularly good at this. Very malleable, so you can hammer it into thin sheets without breaking. Our nonmetals you're going to find in the upper right-hand corner of the periodic table. I'm also going to add plus hydrogen. Hydrogen, even though it's on the left side of the table, is still considered a nonmetal. Most of our nonmetals are gases at room temperature. There's a few solids in there. Sulfur, phosphorus, carbon has some solid forms. And there is one liquid, which is bromine. So on the entire periodic table, there are only 2 elements that can be liquid. mercury, which is right here, Hg, and bromine, Br, at room temperature, I should say. You can make pretty much anything else liquid if you heat it up or cool it down enough. But bromine and mercury are the only two that are liquids. The vast majority of these, though, are going to be gases. So oxygen, fluorine, chlorine, those are gases. Neon, argon, krypton, xenon, those are gases as well. Nitrogen, too. Typically speaking, nonmetals are poor conductors of heat and electricity. The exception to this is carbon. And they tend to be very brittle. So they shatter if you hit them with a hammer. Our metalloid says located along the thick staircase line. So on our periodic table, we have this thick staircase line here. And our metalloids are everything everything that's sitting on the stair. So B, S, I, A, S, T, E. There we go. And then underneath the stair, we have G, E, and SB. AT is 1, 2. So 1, 2, 3, 4. Yeah, there's 7. Okay. So they have properties that are similar to both metals and nonmetals, depending on their conditions. So if you heat them up, they might act more like metals and be better conductors than if you cool them down. There's a short video that I'm going to have you watch after you take your notes here. It'll talk a little bit more about metalloids. They're funky. So when we're looking at that thick staircase line, you might notice there's two elements hugging the staircase that are not highlighted right now, aluminum and polonium. Those are not metalloids. Those are considered to be metals. So when we say exceptions here, that's what we're getting at. Aluminum, I cannot spell today. There we go. Aluminum, Al, and polonium, PO, are metals. Okay. And then I believe last time we annotated the table at the top of page 11 in class. So because I know when this copied, the semi-metals were not super obvious. So yeah, there you go. Good. Questions, concerns, worries, issues? No. Let me know if you have any questions, guys. After you finish with this video, there is one other short ed puzzle video that gets a little bit more in depth into metals, nonmetals, and metalloids. Bye.